Newton's law of gravity within Einstein's context of a curved space-time. We don't have particles accelerating due to some kind of a force or whatever. What we have is mass creating curvature of the space-time in its region. When a particle that is inertial is in that region, in other words, its world line is in that region of space-time, then it picks up a curvature. It's still a geodesic. It's an inertial particle. Its world line is still geodesic, but it's geodesic of the region of space-time where that world line is. We have 3 dimensions of space and a dimension of time, and they're wired together in a complicated way that depends on the amount of matter and the distribution of matter in that region of space-time. An inertial particle ends up having a geodesic world line, as we would have expected. We always expected an inertial particle to have a geodesic world line. We just didn't know about curved space-time. We thought space-time was necessarily flat, and therefore the geodesic was a straight line, so the world line was a straight line. Now that we know that space-time has curvature, then obviously an inertial particle, which has a geodesic world line, the geodesic will be curved or whatever, straight is straight, whatever you want, whatever word you want to use. We're progressively sophisticated perspectives. Okay? Just keep in mind the difference in the ways that we saw things. We started out with just the ordinary concept of inertia that you learned in Newtonian physics. Okay? It's whatever it is. They didn't even speak about what it is. It's a law. We eventually saw it as a world line curvature field in space plus time, where at every point in space plus time you have 0 world line curvature. Particles make sure always to have 0 world line curvature. Then we went one more level of sophistication. We said, no, it's not just a field in space-time. It's the actual definition of straightness in space-time. It's part of the geometrical structure of space plus time. It's not just a field in space plus time. It's part of space plus time. The same thing happened to gravity. We started out with the ordinary picture of gravity as a force. Then because of the equivalence principle, we said, well, gravity, you don't have to think of it as a force. It's an acceleration field. At every point in space, you can define an acceleration. You don't even need the force at all. And then we said, well, you know what? Actually, it's a world line curvature field at every point in space-time. Then we went one more level of sophistication yet, and we said what it is actually is it's a property of space plus time. It's not just a field in space plus time. It's exactly what we thought inertia was for space plus time. It is the arbiter of straightness in space plus time. Okay? It's geometry. Okay, we started out thinking that there was such a thing as inertia and another thing called gravity, which, you know, whatever they're related, not related, didn't really seem essential. And we showed that they're basically the same thing locally, gravity, inertia. Then we said there's no such thing as inertia because you can't shield gravity, etc. Gravity is everywhere. So we got rid of inertia, we said there's only gravity. Now, however, we're getting rid of gravity and kind of going back to inertia, but in a more sophisticated way. We're saying there's no such thing as gravity, there's curved space-time. Inertial particles have geodesic world lines. So particles that are not acted on by, let's say, electric fields, magnetic fields, whatever, nuclear things, etc., going through any region of space-time where there's matter, or matter energy, there's no such thing as gravity. Forget it, it's just a red herring. There's matter energy, it's distributed in different places. It curves the space-time in that region. Free particles with world lines in that region of space-time have geodesic world lines. That's it. That's inertia. That's the law of inertia. Law of inertia is it has geodesic world lines. There's no such thing as gravity. There's only inertia. So first we got rid of inertia and said there's gravity. Now we're kind of getting rid of gravity and saying there's only inertia, but inertia in a more sophisticated way. All right, so now gravity is a chimera. What happens when this world line is in this region of space-time that has curvature? It seems to people who are not aware that space-time is curved as though it has a curved world line. And then they say, well, a curved world line means it's accelerating. It's accelerating means there's a force. Aha, this always happens in the region of space-time where there's matter. Clearly, matter exerts a force on particles. No. Okay? Eddington, who was a physicist who lived, whatever, I don't know, he died, 50 years ago exactly, but he was one of the first mathematical physicists to explore Einstein's theory. He wrote some beautiful stuff. A slight paraphrase because he used some terminology that might be archaic and also that we didn't deal with, but a field of force represents the discrepancy between the natural geometry of a space and the abstract geometry arbitrarily ascribed to it. It's just a beautiful summation. We look at a space and we say, oh, it has this geometry. Why? That's the geometry it has to have. If we do that, we're going to misinterpret things. We say, space-time, yeah, it's flat. We didn't even say it's flat because we didn't even think that it might be curved to say that, no, it's not curved, it's flat. We just assumed that it was flat without even realizing that's what we're assuming, and therefore we were misled into thinking that there's such a thing as a force of gravity. So again, a field of force, in this case really it's gravity, it's not necessarily true about any other force, represents the discrepancy between the natural geometry of space, in other words that it's really curved, and the abstract geometry arbitrarily ascribed to it, arbitrarily meaning just like a priori. Now, physicists at one time, Einstein particularly, wanted to turn every force into something geometrical, but it didn't quite work. Things go back and forth. There's a little bit more geometry, a little bit less geometry. Okay, just to kind of recap, and I think you have this on the notes, Einstein's law of gravity inertia. Okay, and it's not that this term really appears in the literature, I'm just kind of using it. Mass energy gives rise to space-time curvature. Free particle world lines are geodesics of this curved space-time. There's no such thing as a gravitational force. What we're used to calling gravitational acceleration, whether in falling particles or orbits, is simply inertial motion in curved space-time. Okay? In the presence of matter, there's no departure from inertial motion. Particles are attracted to the matter. They don't fall into the matter. Just that in the space-time region near the matter, space-time is curved. The inertial world line in that region of space-time is a geodesic of the curved space-time. And it seems curved in the flat space-time perspective of people looking at it. Again, getting back to the title of the book of which all this is based, it's Introduction to Geometry of Space plus Time's Interaction with Matter Energy. There are two things. There's how matter affects space-time, how space-time affects matter. Matter causes curvature of the space-time in its region. A test particle, which we're assuming is too small, it's just one of our beautiful physics assumptions that purists might hate. We're going to say it's too small to really affect things, so we ignore the effect that it has. We're just going to see what effect space has on it. The effect is its world line, which is geodesic, is now going to be the geodesic of the curved space-time. So you have this effect of matter on space-time, curves it. The effect of space-time on matter causes the matter to move in a geodesic where the geodesic will be curved based on the matter. So it's an interaction between space-time geometry and matter. And of course I put an energy there because later on we're going to add that in special relativity to get the general relativity.